Good morning, everybody. Good morning and welcome to Airborne Gravity 2016. I've maybe a few thank yous to start with, and the first one is to thank all of you for coming. I'm especially grateful to see so many people at what I know is a low time in the industry. I'd also like to thank my fellow committee members who have done all the work. And I'd like to give a very big thank you to our presenters, both the speakers and the poster presenters. These are the people who have prepared all the material, done all the work that you're going to see today. And as well as that, they've written papers for the Geoscience Australia publication, which will form the record of today's workshop. I have to say, we didn't set a maximum size for the papers, for the publication, and we were overwhelmed by the responses. I think we're going to have an extraordinarily good publication as a result of the hard work by all of the people who have written papers. However, we were hoping to have that available for today, and we just simply have not been able to get that done in time. So my apologies for that. But we decided that we wanted the quality of the publication to match the quality of the submissions. And so it's going to be a little bit delayed. It'll probably come out in about a month or so. We do have the email addresses of all of the registered attendees. So we'll contact each of you once we've got the publication ready and organise to get it to you. Anybody who hasn't registered, wants a copy of the publication, come and talk to one of the committee members during one of the breaks. Okay, so that's really it from me, although I do have a few final comments. Firstly, we could all just make sure that our phones are sound muted or switched off. Secondly, please make sure you don't miss the posters. They're just outside the door, and we're going to have time to have a look at all of those during morning tea and lunch and just before lunch. So please make sure you go and have a look at those. There's some really excellent and interesting papers there. And finally, I just want to remind all of the speakers of the need to keep to the time requirements. There'll be a warning given a few minutes before the end of your talk, and then at the end of your allotted time, you'll be escorted from the podium. All right, so without any further ado, our first talk is from Lockheed Martin, which shares some insights into advances in their airborne gravity technology since the last Airborne Gravity Workshop in 2010. Their improvements bring us a step closer to removing instrumentation as a limiting factor for airborne gradiometry. Our speaker is Tom Meyer, who some of you may already know. He is a corporate Lockheed Martin Fellow, the Gravity Systems Manager of Advanced Engineering Technology since 2007, and has been with the Gravity Systems Group for 18 years, authoring nearly 24 US and international patents in the areas of geopositioning and ultra-precision instrumentation for exploration. Tom.
Thank you. How do I get this onto the screen?
Oh. Sorry. I knew there was something I'd forgotten. So press that to go forward.
Okay.
Red dot for the pointer.
Okay. Thanks. So we're going to hear from a few methods of measuring gradients this morning. I'll start by just really quick conveying the crux of what we do at Lockheed Martin to measure gravity gradients, and talk about the challenges we face and how we overcome them, and then get into specifics regarding our standard product offerings, some improvements, as well as a recently designed digital FTG system that fits into a helicopter, an enhanced FTG system, EFTG, that's now available through Austin Bridgeport. It pretty much sets a new performance standard for airborne gradiometry, as well as something we have in development with CGG called FTG Plus. So we measure differential gravity, and essentially just difference 2-point-wise acceleration measurements and divide through by the baseline distance. It's a hardware implementation of a spatial finite difference. By doing that, depending which way your sensitive axes are facing, you either get your long axis gradient or one of two cross-axis gradients. That's shown here, one equation. Whoops. Oh, okay, so we measure the left-hand side there. Gravity, this would be maybe a forward down, G sub Z at some distance forward, x plus del x minus the distance back a ways. Divide through by the baseline, you got an approximation to a forward down gradient. The takeaway here is that as you increase the baseline, the measurement noise being the same for the core sensor, you get an increase in your signal to noise ratio. So the name of the game is get a bigger baseline if you want higher sensitivity. Unfortunately, there's a few practical challenges. Reality. That sort of measurement is simple, it's sounding, but it can be completely overwhelmed, as can any gradient measurement method, by things like non-inertial motions, like the deviatoric of the angular rate is traceless and symmetric. It feeds through just like the gradients do. Geometric instabilities, structural deformations of your platform, your instrument, while it's under motion. Those sorts of misalignments, those dynamic effects get rectified back into your instrument's passband, as well as thermoelastic deformations. Right, nothing's at a constant temperature. Those perturbations have effects structurally, again, rectifications into the instrument passband, as well as a whole slew of very sensor-specific or intrinsic errors. For us, this would be things that are specific to our Model 7 accelerometers. For others, these are, I'm sure, largely the same, but also some very specific ones to those sensing technologies. And you got to get your data stream logged in your computer, so the whole signal acquisition process introduces more contamination. So there are some common methods to mitigate the unwanted errors. First, you eliminate disturbances at the source by choosing a vehicle that is amenable to your system, that is maybe more stable than others or can be operated in a stable manner, but there's limitations to how well that can be done. We try to isolate the instrument from its surroundings, both mechanically and environmentally, so we put things on a stable, leveled, pointed element. Historically, we've always put that stable element inside a series of nested gimbals to isolate our instrument from rotational motion of its host aircraft. And we set that whole configuration on a passive suspension to provide some isolation from the lineal motion. That doesn't get you anything at low frequency though, because the vehicles that everyone uses don't offer the sway space you need to take up meters of linear motion. So it's only for the higher frequency disturbances. And an environmental enclosure, thermal isolation, acoustic isolation, whatever you can manage. The third layer, I guess, would be to monitor and compensate for the effects that you don't want. There's some obvious choices. You can measure the angular rate of an instrument block and with gyros and try to back out this motion. But it's not feasible for a lot of things, especially thermal. Thermal by nature and measuring gradients and to the fidelity that you would need to, it's just, you can't do it, period. Then there's some Lockheed Martin specific mitigations for our systems. We exploit common mode rejection to the nth degree. I mean, we really get everything we can out of common mode rejection by pairing up accelerometers and trying to basically negate or buck out lineal motion in particular, as well as some angular effects. And spectral separation. So you're probably aware our gradiometers are rotating accelerometers. By doing that, we mechanically modulate the hardware, and that kicks the gradient signal of interest out away from DC and all the low frequency errors that are the toughest to deal with, and gravity, which is by far the biggest input, plumb G. Okay, I lied. I guess I have one other equation here. It says success equals good execution of fundamental principles plus a few clever insights along the way. So in one sense, in that sort of broad sense, nothing's changed in the past 6 years. There's no magic. This is still what we do. I didn't come here to stop at that. If we talk about some of our standard systems, we continue to make improvements to what we call either our standard or legacy systems. The normal sort of stuff that you would expect during the life cycle of a maturing technology or product. And we do this through OSM, operational support and maintenance, that we have with our customers, sustainment activities, R&D, things like newer improved regressors for denoising data, better diagnostics, data logging, and you can read a few more. The takeaway, though, is that these things might seem really small and incremental, but these modest changes can be a big deal. Some of this stuff really keeps the system flying and performing out in the field, and it can take 1 million line kilometers to recognize that a need or opportunity even exists. This doesn't go out day one like that. I mentioned a recently designed digital FTG. This follows the approach that we used to achieve similar benefits for digital Falcon, or where we really cut down quite a bit of the size and weight. SWAP is size, weight, and power. And increased reliability. You can see the analog system on the left there, and its counterpart, the digital system on the right. 40% weight reduction, 30% volume reduction, some hardware changes, fewer connectors, higher reliability. eFTG is the enhanced FTG. It's a physical upscaling of the existing full tensor gradiometer architecture. Remember I mentioned bigger baseline, higher sensitivity, better SNR, signal to noise ratio. So this has 3 gradiometers in it, a full tensor configuration. Each one is roughly twice the size of the standard full tensor gradiometer. It also has a second complement on each of accelerometers on each gradiometer for averaging down certain errors and doing some quality control checks. It's shown here on our fixed wing 6 degree of freedom motion simulator. And it performs on that simulator to a level of 6 to 18 E squared per hertz. So that is essentially a new performance standard for the industry. Services are now available through Austin Bridgeport for that system. A small example donated by Bridgeport and Gary Barnes in particular. Undulating salt layer with diapirs. The model and a clean signal compared to standard FTG. You can see there's a better uplift of both the long and short wavelength signal on the right-hand side there. There's another example regarding kimberlites in the paper. We also have some new lofty objectives. FTG Plus, which is product outgrowth from R&D over the past several years. We've been looking at ultra-low frequency improvements to our core Model 7 accelerometer. And the objective here was really to maximize what you can do with our core sensing technology, the proven sensor, what you can do in sort of the same operating envelope as a Falcon system. It's a new platform altogether, a new architecture altogether, very much blank sheetish. It's based on a spherical air-bearing platform. We strive to have as much monolithic construction as possible, cutting down on both mechanical and electrical interfaces, points of failure. We've given a lot of athermal design considerations to the system, deliberately designing in acoustic isolation and lots of other stuff. The performance goals for this FTG Plus instrument are 1/4 E squared per hertz over a passband of 0.1 millihertz to 1.5 hertz or greater. We set it at 5, above 1.5. It might not be much use right now, but. The development team comprises CGG Multiphysics, who sponsors the continued R&D of this project. They provide deployment expertise, reality checks in the way they use the system. It's nice to sit back and assume it's going to be used certain ways, and then you find out it doesn't happen like that. So that's good. Keep us on track. And especially helpful is all the data that they've provided for both fixed wing and helicopter. Not the mundane stuff. We asked for the nastiest data. We're designing for the worst flights they've ever had. We want to be immune to turbulence up to whatever the pilot can stomach, literally. Lockheed Martin Space Systems Company has been brought in for the project. This is a corporate-wide sort of initiative. Part of my job is to put teams together and put them on new projects like this. In particular, the Precision Pointing and Controls Group, who has a lot of experience with air bearings, and the Thermal Sciences Group. And us guys, you know, at Lockheed's Gravity Systems, working on the improved core sensor and having the instrument design and manufacture expertise. Some of the design highlights, well, I'm showing the model here in a B-3 helicopter, just because that's the toughest one to get it in. There's lots of room in fixed wing. And we're going to get it in this helicopter. Some of the design highlights include non-rotating accelerometers with the maximum baseline. So the accelerometers are near the periphery of what you're seeing in that model there. The spherical air-bearing platform, it has non-contacting sensing and actuation. All custom stuff is needed. You can't couple, you don't want to couple across that air-bearing interface. There's only a very minimal tether for power and comms. The air-bearing intrinsically has isolation down to DC. You don't want to destroy that. 60 dB stuff, which you can double 120 dB or greater against the angular, the jitter terms essentially. So you want to preserve that. Concentric retrieval of all the tensor components. I say internally balanced with ideal conditioning, meaning we're measuring pairwise sums, and by ideal conditioning I mean when you use those to then get your full tensor, the geometry and other design aspects of this thing are such that you don't amplify any noise or errors. Normally you do, you can't, but we've addressed that so we don't here. Ambient temperature use, and it's designed from the ground up for exploration. It's an example provided by CGG, Mark in particular, based on interpreted seismic data. The client gave 3 horizon picks and converted to depth and integrated those into the model with well-logged data. Basically a shifted block model. The modeled response, a clean response shown on the right here. There's no scale, but it's roughly 8E peak to peak. Compared against Falcon Plus, shown on the left, using a 1 kilometer low pass, 2.2E standard deviation. FTG Plus properly reconstructs the signal. So in summary, we do work to improve these systems all year, every year. We have a newly designed digital FTG, smaller, lighter, fits in a helicopter, setting a new performance standard through eFTG, and the FTG Plus, an entirely new non-rotating architecture on a spherical air-bearing based platform, unprecedented stability, etc. So I'd like to just thank Austin Bridgeport and CGG for providing the examples. Again, there's a couple more in the written abstract, and express gratitude to the committee for putting all this together and still slaving away on the written paper. Thanks.
Thanks very much, Tom. Very interesting talk. Our next talk is from Chris Van Galder on the combination of airborne gravimetry and gravity gradiometry. Chris is an engineering physicist who started in exploration a little over 12 years ago and has worked almost exclusively with airborne gravity and airborne gravity gradiometry. He started with Standard Geophysics, working with their airgraph system, and moved to Fugro/CGG in 2006, and has been working with the Falcon systems ever since. Chris is currently manager of the AGG department and is in the process of moving from Toronto to Perth. Please welcome Chris.
Thank you. There we go. All right, so I'll just go over the three things I hope you all take from this today. I'm presenting three improvements to our standard Falcon technology. The first will be introducing a new technology we are adding into our Falcon offering to help improve the long wavelength gravity detection. The second will be a new processing technique that improves on the wavelength at the shorter resolution of our signal. And the third is an initiative to take advantage of the fact that we've been working with these technologies for the last decade and to offer a lower noise product. Over the last number of years, we've been working on an R&D project to introduce a gravimeter with the Falcon gradiometer systems. This is the culmination of that R&D. It's the first commercial strap-down gravimeter. It's designed to handle typical Falcon acquisition conditions, drape flying, moderate levels of turbulence. There are no moving parts, and it's small and lightweight. It's always hard to see how these things are, so we put a pen in there. It's basically designed to not take away anything from a Falcon system and still provide the response we require. So we've tested this flying east of the Ottawa airport. We did a 120 kilometer long repeat line. We flew it 14 times across 3 different flights. We're looking at signals that the Falcon system needs help detecting, so it's very long wavelength gravity. So results here using a 400-second filter, which at standard survey speeds is about 24 kilometer resolution. The repeatability of all these lines is about 0.6 milligal, which is what we were aiming for. And it was flown with an undulating drape at a constant altitude of about 300 meters. And the undulating drape was just a sinusoid pattern at plus or minus 200 meters. We then flew a test area just beside the repeat line. And what we have here, just 2 sets of filter results, 18 kilometers on the bottom and 24 kilometers again on the top. And you have ground gravity data of about 1,800 different gravity stations. The S-grav data is in the center, and then just the difference between the two. When we difference them, we get a comparison called ground truth, and at the 24-kilometer filter we're looking at, we're getting a ground truth of about 1.3 milligauss. Moving to the shorter wavelength, we've also been working on our processing techniques. So what we're calling enhanced processing is a means to exploit how the data is acquired. If you think about how we fly surveys, the data along the line is sampled at a much higher rate than the line spacing. And by increasing the cutoff frequency of our filter, we can linearize the acquisition noise along the survey lines, and we've designed specific filters to remove that acquisition noise while retaining higher resolution geologic signal. This is an example from coring. So the line spacing here was flown at about 100 meters. On the left, we have the vertical gradient response using our standard processes. In the center, you can see the enhanced product. And on the right is simply the difference between the two. And you can see the signal that's being removed is very linear and likely not very geologic in nature. And as a result of this, we've been able to cut our noise power by half. This is a spatial PSD of the two grids we saw before. And again, you can see the enhanced processing product does retain signal, much shorter wavelengths than the standard product. We've then taken this and expanded it to more wide space data. So with the wide spacing, 250 meter spacing and above, it's not the same process. It's not as easy to linearize the noise at these, the wider spacing, but by applying the same enhanced processing, we're able to decrease the noise power with sacrificing only signal at a maximum of 2 line spacing. So here again, on the top left, you see the enhanced product. Underneath that would be the standard product. This is the vertical gradient again, and the difference between the two. So in the difference, you can still see some linear geologic features, but on the whole, it's basically just high frequency noise. And we've been able to, in this case, we're able to drop noise power by about 1/3. So here you can see the spatial PSD again, only this time the enhanced product hits a 3D point about twice the line spacing, or 1 kilometer. The third endeavor is called Falcon Plus. We released this a little over a year ago. Over the last decade, improvements in both our system design and our operational experience, we've been able to reduce our noise levels by half, and we're able to install these systems into helicopters and smaller fixed-wing aircraft. Taking the average noise of a number of survey lines over a number of years in a number of different conditions, what you have here are the average noise along those survey lines for Falcon in blue and for Falcon Plus in green. So you can see at any level of turbulence, the Falcon Plus values are about half the Falcon. When the data is acquired and processed, the results are a more coherent, lower noise product. This is just a synthetic model. On the left, you have the standard Falcon product, and on the right, you have what the Falcon Plus product can offer. in summary, I said there were 3 things I'd hope you took away. On long wavelength gravity, we've introduced the S-graph. I've shown the repeatability with repeat lines was 0.6 milligal at a filtering of 24 kilometers. We achieved a ground truth of 1.3 milligal using that same filtering at 24 kilometers. For the short wavelength improvements, we're introducing our enhanced processing. It reduces the acquisition noise. It improves resolution for surveys up to 200 meters in line spacing and decreases noise powers across the board. And improvements on our existing technology, we've rolled out Falcon Plus, which halves the noise of standard Falcon survey, smaller footprint and weight. And all 3 of these things, we're rolling into an initiative called Full Spectrum Falcon. And I will be giving another talk tomorrow going over Full Spectrum Falcon with some examples. So I will encourage you all to come back again tomorrow and hear that talk. I'd just like to thank everyone here for listening to me and the committee for inviting me. And I look forward to seeing you all tomorrow. Thank you.
Thanks very much, Chris. Our next speaker is Brian Main. Brian started his career drilling and testing oil wells off the coast of West Africa. He has a BSc in Mechanical Engineering, an MBA, and is also a graduate of the Directors Program at the University of Toronto. He is a co-founder of JetX, a company created to develop and deploy new transformational Earth imaging technology, with quite naturally high-resolution airborne gravity gradiometry at its core. Brian currently serves JetX in the role of VP Business Development and New Ventures. Please welcome Brian.
Thanks, Mark, and thanks to all the organizers as well. Title today is Improvements to the JetX High Definition Airborne Gravity Gradiometer. The title in the program mentions first data from the JetX HD-AGG, so I will definitely be presenting some data here. So we would have preferred next month because we are expecting, as you'll see in the presentation, much better data coming, but the organizers wouldn't allow us to push the conference by a month. So anyways, what I'm going to do today is I'm going to do a quick review of the system for those who are not familiar with it. And then I thought I'd structure it by just simply talking about the past, present, where we are today with our new 2-axis system, some results, and then what to expect in the road ahead. So first, a quick review of the system. It was designed to deliver enhanced performance down to the 1 EDVOS per square root hertz performance in airborne, as has been desired by our strategic partners in the industry for a long time. To do this, we took a different technical approach. We took a cross-dumbbell gravity gradiometer, which is cryogenic, which has a lot of advantages, a lot of challenges as well, but that instrument sits inside a cryostat at liquid helium temperatures, which then is supported by a proprietary isolation system that also uses air bearings. And then it's surrounded by a bunch of, obviously, data processing. Now, we haven't done a lot of focus on the processing afterwards, but we are able to turn around data within a day or two. So just a little bit about the instrument itself. Unlike the accelerometers, we are using the cross-dumbbell approach, as shown on the right. So by first order, it does not respond to translational or rotational accelerations, but will scissor to a gravity gradient. But as Tom mentioned, there's all kinds of challenges, so that's pretty simple in principle. But one of those accelerometers, as shown on the left, is actually machined out of pure niobium, which is superconducting at liquid helium temperatures. It's EDM machined all the way around there, and you see there's a little pivot in green there that one of those angular accelerometers will rotate on, and it's got to be balanced, the center of mass to the center of rotation to within a nanometer or to 1/1000th of a meter. So I thought I'd, for the layman, look up what a billion is, and first thing, of course, I come across on the internet is the rate at which the U.S. spends or prints money, and in that, it only came out to 8 hours and 20 minutes, but when you looked at seconds, 1 billion is 32 years, so that just kind of gives you an indication. And that rotation of that beam that we have to measure for 1 EDFOS is less than the size of an atom. So another analogy is to take the diameter of your hair, divide it by the distance to the moon, and it's roughly 50 times smaller than that. So that gives you, that's just some of the challenges, because there's a lot more, but as Tom mentioned, the whole system, but there's a lot of challenges involved. So a little bit of history. I thought, what better way to align the history in terms of using the ASEG as guideposts. You can look at our papers presented in the last number of years. I actually presented in 2000 before the workshop started, where we had our design in place, and then when we were here in 2004, we had the initial design of all the subsystems in place, and we had actually built and tested the isolation mount. Then come ASEG 2010, we had completed and built subsystems, and we'd flown the subsystems all on their own, but we had not yet flown the entire system, which we're about to do. Fast forward to today, we've rebuilt the gradiometer. We've made a substantial number of improvements, which I'll talk about, and further flight tests are underway, and we plan to be commercial this year. So, oops, the wrong way. Looked at it another way, 2000, 2004, right at the beginning, we were, had all our licenses and technologies in place. We were very inspired. We thought it would only be a year or two before we were flying the gradiometer around the world, helping to reduce the discovery gap in minerals and oil and gas. And we are confident that success was just ahead. Unfortunately, it was a much longer road than we ever anticipated. And so in now going to 2004 to 2010, we were about to fly the system. We had very high expectations. And we thought, well, there's a great demand for the system. But we found out that actually there was no, it was very difficult actually raising money. And this is actually an important point, because JetX itself has no revenue. It doesn't have the military behind it. We've been had to go out and raise all the funds privately. And this is a full-time position in and of itself. So, but anyways, between 2004 and 2010, we did have a lot of detours in the technical development plan. We've had leaks in cryostats, which caused months of delay. We had coils delaminating due to the cryogenic, the constant changes in temperatures. We had manufacturers changing their process on us on materials that didn't tell us, and then it took months to discover. So there's been a lot of challenges along the road, but nonetheless, there was a lot of milestones that were made. And then again, coming up to just the last time we talked here, we had very high expectations about the fly. And well, our expectations were not met. When we first flew the system, we were hoping for to get down to results that we were achieving on the flight simulator. There was a lot of challenges ahead, but nonetheless, we were very encouraged by the results. So there was no showstoppers. We realized that there was some things we had to do We were flying the gradiometer instrument that we had received from the University of Maryland. So what we did is we rebuilt that gradiometer and put it together with the rest of our system, and we were confident that success is just ahead. So in summary of the past, anyways, this is kind of summarizes very neatly here. I mean, it was many years ago, 2000, we thought we were going to be flying within 2-3 years, and it was just been a lot more challenging than we ever anticipated. Nonetheless, we think we're very close to the finish line now. So a little bit about the developments since 2010. We've had 3 series of dozens of test flights, with each time making modifications in between. That's not a steam-driven aircraft. That is, we had to cut a hole in the top of the fuselage to top up the cryostat with liquid helium, so that's what you see there. The isolation mount, which I mentioned, is air bearing. We figured air bearing is the way to go. We haven't done a lot of improvements there. We're quite satisfied with it. We have improved, what we have done is improved the angular velocity measurements by a factor of 4 since 2010. And our approach has been, if it's good enough, just leave it. I mean, obviously the engineers want to continually improve things, but if we're at the point where we think we're going to be good enough to get to a commercial performance, then we kind of put the desired improvements off to the side. And we've got a lot of those planned for the next system, but for the time being, the isolation mount has been pretty good. The flight cryostat, we've improved the temperature control. It's you got to control the temperature down to microkelvins, and we've managed to improve that by a factor of 3. We've also stiffened the support inside. We found that the gradiometer was, even with the isolation system, the gradiometer, with the measurements we're trying to achieve, we needed to stiffen the support up because it was moving too much with inside. The instrument itself, we rebuilt. So I'll talk about that in more detail, but we reoriented. So now we have 2 components. We measure GZZ minus GXX and GZZ minus GYY. We have improved the balancing, the center mass, center rotation, by a factor of 3. And we have improved the residual corrections, both temperature, translational, and angular accelerations. And we've also tremendously improved the performance of our squid controllers. So just very quickly, the instrument we received from the University of Maryland was a single-axis system. Those angular accelerometers were oriented in the horizontal plane, such that it would measure GXX minus GYY. More technically speaking, it's 1/2 GXX minus GYY, but one on top and the other one will be 180 degrees on the bottom, as shown there. The advantage of this, we thought, is the beginning anyways, is that the accelerations in the vertical direction are much greater in the aircraft, and this, in the gradiometer oriented this way, was less susceptible to the accelerations. So that's was the advantage. The disadvantage, of course, of this system, when it's only one single axis, is it would be blind in practical conditions to geology in certain orientations. So if you look here and you have 3 tabular bodies in the XY and one aligned at 45 degrees, the GXX minus GYY wouldn't actually see that, the one aligned at 45. And even if it wasn't 45 degrees, once you start adding noise in there, then it's going to be blind to geology in certain orientations. So we, in the second system, our commercial system, we created the 2-axis, and both were downward looking. So one is measuring GZZ minus GXX, and the other GZZ minus GYY, as shown in the diagram there. The advantages of this is that with the downward looking components, there's certainly not, it's not blind to any geological orientation, and in fact, in one axis is highlights the one direction, and the other one will highlight in the other direction, such that you combine the two, you get a 37% lower noise. And in addition, with the two, we can calculate GZZ at a single point. So we don't have to fly the whole survey and use various methods to recalculate GZZ. We could just use add them algebraically and use Laplace's equation to get GZZ. So that's another advantage. So some results. So this is from our single axis prototype that we flew. We found each time we would test fly it and then we'd move it up into the air, it was roughly 2 orders of magnitude twice as, the noise levels were twice as high as what we had on the flight simulator. So that was the single axis prototype, and then we've rebuilt a commercial system with the 2 axis, and the team wanted to make sure we got down well below 10 atVos per square root hertz on the simulator before we took it into the air, because we were expecting twice. As you can see, we finally got down to around 8. And so we took that system and flew. This was going back at the time the organizers were putting this together. And there was some, should we fly or not, because number one, we only had one axis working. So we only had one axis in this result, and also there was a bunch of other changes that we wanted to make, but it had been a number of years since we actually flew the system. So the decision was made to take that system and fly it. So we did land up getting, as expected, around twice. So we got around 15 atVos, but that was with one component working only. So we expect that with improved, well, I'll just flip the next slide here, expect that the road ahead, what we've done now is we're making minor modifications. So since those test results, we've warmed it up. We're doing further improvements to the center mass balancing. And we have the second component operational now, so that'll give us additional benefits in the processing. And so we're flying again in September, where we expect to get below 10 atVos per square root hertz in the Caravan. From there, we've got some test sites lined up, and we plan, if we achieve those, to move it into a -8, where our target is below 5 atVos per square root hertz. And then we have additional modifications and to finally deliver our objective of 1 atVos. So to show some data, we don't have a test site near our airport in Brampton in terms of a ground truth. We eventually hope to get over here in Australia in their -8 to fly the RJ Smith site. But what we did is, the engineers are saying, don't worry, we're measuring signal. We're always going, well, is the drive down the noise? Are we going to be, eliminating signal? So this was just a sequence of an area where we did have some ground information on the train. So the train is shown there in the bottom, and then the top is the computed train response and our instrument GZZ, and again, this is only with the one component operational. So it's just to show that we are measuring the signal as well. So in summary, it's been a long, challenging journey. There's been tens of millions spent over 16 years of development. We've made major advances since the last workshop here in 2010. Namely, we rebuilt and have a new 2-axis system. We've made improvements to our subsystems, the processing, all the auxiliary measurements that go into making the corrections. We've achieved good performance with a single component only, and we're expecting better next month and targeting to be commercial this year. Once again, I'd like to thank the organizers and thank you. And I should say a special thanks to the JetX team who's done all the work behind this and are able to be here. Thank you.
Thanks very much, Brian. All right. So the last talk in this session will be presented by Frank van Kann, and he'll be giving us the latest news on the VK1 gravity gradiometer being developed by Rio Tinto and the University of Western Australia. Frank is Winthrop Professor of Physics at the University of Western Australia and the inventor of the VK1 Airborne Gravity Gradiometer, with the original prototype beginning development in 1980. He holds more than 200 international patents. Frank is presently on secondment to Rio Tinto in the role of Technical Director, VK1 Technologies. Please welcome Frank.
Left and right, yeah. Okay. Thank you. Okay, so nothing's possible without a dedicated team, and right at the beginning I'll express my appreciation for the team members. Okay, so in the context of, we've seen, I'll go through this fairly quickly, we've seen different types of instruments. This is one type of instruments where you have two accelerometers and you measure the difference between them. We've seen that described. There are some problems with that and you can overcome them with good technology, as we've heard. We've chosen the beam balance method, which has some intrinsic advantages because the beam is very rigid and you don't have to worry about the dynamic range of your transducers so much. Okay, that was a stick diagram. Here is reality. This is what it really looks like. It's a beam balance. It's balanced to within 5 nanometers. So the question is, which atoms, hands up the atom that's got the centre of mass. And we've blurred out the magic micropivot, not because we're going to censor it, because actually you couldn't see it properly on that picture, so I've shown a zoom in of that, and makes the point where you've got your centre of rotation and the centre of mass separated by 5 nanometers, and shown there also are the transducers, superconducting transducers. Like the previous speaker, this is a cryogenic device, and that measures to the 1,000th of the diameter of a hydrogen atom. So what I have learnt in the past 30 odd years is that gravity is a very weak force. But the one thing that gravity's got, that there are no negative masses, and so therefore you can't have gravity shields. The Earth is astoundingly opaque in any interaction other than gravity. It's totally transparent to gravity. So that's why all of us are here working so hard to make this work, because gravity is the only thing that you can make the Earth transparent with. But it's difficult. 10 orders of magnitude between the dynamics of the platform that you're operating in and the measurements that you have to make. 10 orders of magnitude. It's crazy. Why are we doing this? So what are the strategies that we employ to do that? And the first thing, as I said, you balance the beam balance extraordinarily well. Now, I've only said we get a factor of 1,000,000 there. That corresponds to 50 nanometers of imbalance. Let's be a little bit pessimistic and give ourselves some margin for improvement in the future. But that's enough. So the next thing, it's 6 orders of magnitude is not 10, so we need to find some more. So the next thing is what I call electronic balance, and to explain that, let's have a look at the system. There are the sense coils and the squid sensor, which measures the angle of the beam, and that's your gravity gradient signal. We already have electronic damping, because the Q factor of this pivot is beautifully high. It needs to be to keep the thermal noise down. And so that means you can very easily take signals from linear accelerometers and do electronic balance, which is sort of equivalent. What we do with the mechanical balance is we tweak the little balance screws to move them in and out to shift the centre of mass. With this electronic system, you do the equivalent of that using the acceleration itself to correct the residual imbalance. And that gives you another factor of 1,000 or so. You can probably do better, but let's be pessimistic and say only a factor of 1,000 available there. And then finally, you do the numerical processing. This is really the place where I think the future lies. If we're going to see dramatic improvements, I think we all are finding that the big improvements are going to come from doing smarter processing. Okay, so that was the translational acceleration problem. That's 10 orders of magnitude. The rotational one's only 8, so I'll go through this one pretty quickly. So your equivalent motion of the aircraft is about 10 to the 8 ETFOS in terms of angular acceleration. And like everybody else, we have a stabilisation platform. We're only expecting a gain of 100 or so from that. It actually does pretty well. And then nested gimbals, I've heard mentioned. Yes, we have nested gimbals. There's a miniature stabilisation platform inside the cryostat, inside the liquid helium space, and that gives us another factor of 1,000 or more. You know, being conservative, factor of 1,000 is all I'm going to claim. And then again, as Brian mentioned, there are 2 beam balances and the beams are orthogonal to each other, and that gives us some more common mode rejection. And that means we can get the 8 orders of magnitude with these things. And I haven't mentioned anything about numerical processing. It's not really required for the angular disturbance. Okay, where were we in 2010? Well, we'd just done our first shakedown flight. Didn't get much data on, but we learnt a lot, you know, we really did, and we learnt we had to do everything. Again, we had to improve the learnings were like this triangle. The apex was a small job and the base is a really big job. That's what we had to do. We had to improve the instrument a little bit, not much. It was actually pretty good already. We had to improve the stabilisation platform a fair amount. Again, it's a long journey, and I won't discuss that too much. We had to improve the data acquisition and the control, and the big thing is the data processing. And what we learned also is you needed to do a lot more dynamic testing, a lot more flights, a lot more dynamic testing. We've done a lot of dynamic testing since then, and we've really made enormous improvements to the system, which I'll show you the results of as we go. So dynamic testing, well, it's a very important thing, so I thought I might just introduce the kind of dynamic tests that we do, and I think we all do. There are 3 platforms. There's the flight simulator, the hexapod, which you can do in the lab, and it's really good for all those reasons. It's expensive, it's convenient, you can do it without going anywhere. You just put your machine instrument on the hexapod and take it for a joyride. But the other thing is you can also do specific experiments. You can synthesize motions to give you an understanding of how your apparatus is working. The second thing is, well, the disadvantage of the hexapod is it can't get down to the low frequencies. The hexapod's just not big enough, the room's not big enough, the building's not big enough to get you down to the low frequencies. So a van is a good substitute. It's pretty inexpensive still. It's a better frequency range than the hexapod, and it's not that inconvenient. And it gives you all of the turbulence you need, but on different axes. So it's not quite the real thing, which is the aircraft. And they're the obvious disadvantages of the aircraft. You've got to mobilise to the nearest airport, and it's expensive to run, and so on. But at the end of the day, that's reality. So, dynamic testing environment. Here is the issue. The red curve shows you the turbulence spectrum from sort of a moderate turbulence flight, and that's as the scale of turbulence as defined by Dransfield in a paper in 2010. We're using that scale, even though probably it's not the right frequency band to characterise how our instrument operates. We probably should take it a little bit lower, but nevertheless that's a yardstick that we all understand, so let's use that one. And we can simulate a 60 milli-G line which follows the red line pretty well, except at low frequencies. Compare that to the van, which is there. Oh, by the way, just in case you're wondering what a milli-G is, 60 milli-Gs is 0.6 metres per square second. So the van does give you some more turbulence at low frequency, has a little bit of a gap there in the mid-band, but the other axes contribute a lot more than they do relatively in the aircraft. So I think the pale blue line is kind of a measure of what you get in a road vehicle. So the stabilisation platform has been quite a journey, and it's working pretty well now. This is a spectral measurement of the residual motion during a flight. Actually, I think it was during a van test, but it's very similar. And just to give you an idea, I've put a dotted line there, which is the line for 1 ETFOS of centrifugal force error. Now, I know it's hard to put a square law curve on a spectrum, but just to give you an idea of where it is, and you say, oh, gee, it's not good enough. Well, don't forget, we've got another stabilisation system with a gain of 1,000, so it's actually more than good enough. Right? And right there, where the internal stabilisation system works best, is in that band. And you can, I guess the other thing, how am I doing for time? Yeah. The other thing I should point out that your axis is the worst. That's the one that's got the most bearing friction, and but you know it's still good enough. So I think the platform is a very nice story, although it's been a long road to get there. So before we can talk about dynamics performance, I guess we know that the best you're ever going to do in a dynamic environment is what you can achieve when you're not moving in a station. So here it is in the lab, sub-ETFOS per root hertz, and this is just a sample taken just before we're ready to do a simulated flight. So everything's ready for takeoff. You get the same static noise whether you're in the van or in the aircraft. And there's nothing magic about the timer. In case you're worried, 5 o'clock in the morning, oh, no wonder you're getting good results, it's all very quiet. No, this is GMT, and we're 8 hours from that. So it's actually right in the middle of the day where everyone's stomping around, and you know, that is the standard static noise that you get from this instrument. And then, so let's start talking about dynamic environments. The flight simulator is the first port of call. So we have a 60 milli-G line, and one of the disadvantages of the hexapod is it's close to the ground, and you've got the gravity gradient of all the stuff in the lab to worry about. We know that, we've mapped that, and so the green line is the known gravity gradient, the purple line is the measured signal, and the red line underneath is the difference. That's a bit disappointing. It's 9 ETFOS RMS in the 1 hertz bandwidth. So it's clearly a little bit of work to do, but it's still a fairly satisfying result. And one thing that I want to emphasise is that if we do another advantage of the hexapod, it's totally reproducible. We can do the same flight over and over again, time and time again. And if we take, say, a dozen lines and take the mean of those lines and then look at the deviation from that mean, you find that it's 1.8 ETFOS. And therefore, it tells us we've got to work a little bit harder on our processing, because we should be able to get, the instrument itself is reproducible to that level, so we should be able to get down to that level if we just a bit smarter on our processing. And this is fairly recent data. That's the journey that it's been. So we started off with much worse noise level, and that's a log scale. So the improvements are happening linear time scale, logarithmic noise scale. So the arrowheads are very seductive. So van is the second set of, and again the van has got issues because you've got real gravity signals to worry about, and we've got a test site. It's a historical test site just close to the university. It's easy to get to, and it's got we're driving along the river beside a cliff. Well, it's not really a cliff, but it's a sand dune, effectively, and it has some gravity signals. And it's difficult to establish the ground truth, unlike in the lab where we could map out the gradient. Here we have to just imagine what it might be. And I think there the only way we can do it is using the reproducibility. So we drove the same line many times, and you can see there the mean of our runs and the departure from that mean, is certainly less than 10 ETVOS RMS. So that is really not the final answer on what the noise is, because you can see some outliers there. When you're driving along the road, you've got traffic, you've got to deviate around parked cars, you've got big heavy trucks, 20 ETVOS trucks driving past you. So it's pretty tough. And so some of that departure from the reproducibility is due to things that beyond your control. But nevertheless, it's a great shakedown. If you get down to this level in the van, you know it's worthwhile spending the money on sticking it in the aeroplane, which is what we did. A number of times we went out in December 2014, and we learnt a lot. We didn't get any really good data, we got some. We went out again in April with a much improved system, as you can see. Again, some tweaks had to be made, and we went in July. We're still processing that data, but we've got some results from that, which I'd like to show you. So we went to the R.J. Smith test range, which is only a couple of 100 kilometres away, and flew, and it's a bit difficult there because there's houses and farms, and you've got to find a path that you can fly that doesn't offend any of the local farmers. We did actually have to have one sacrificial sheep. We managed to get a sheep tangled with a barbed wire fence, and it had to be put down, which is very unfortunate. But anyway, so one sheep was sacrificed to achieve this really good result. So that's the first line we flew, and then we flew the same line again. I guess I should this is the April data, where we realised that we needed to make some improvements. So the April data, we filtered that down to 0.2 hertz, so I should point out that, and it's about 40 ETVOS. Then we went again in July, and we did a lot better, as we expected, up the bandwidth to 0.5 hertz, which is pretty much our standard bandwidth if we're sampling at 1 hertz. That's the anti-alias filter for a 1 hertz sampling rate. And there we did a lot better, and just to prove that it's not a fluke, we did the same thing again a little while later, and we got very, very similar results. So I guess that's the results that I'm quoting in the 0.5 hertz bandwidth. It's sort of 13 ETVOS, and there's the flight path that we flew. It was a constant altitude. We didn't try to drape in this case, and just I guess because we have to learn how to do this, we've done the topographical correction. So we've drawn the raw gravity signal in the top graph and the terrain corrected gravity signal in the bottom graph. Of course, it doesn't look as good in the bottom graph because we've subtracted some signal but kept the same noise. So along the way, as you can imagine, there have been some issues, quite a few. We're going to just touch on a few. How am I going for time, Mark?
You're fine.
Yeah? Okay, we've had a few. One of the crazy things is we had this stabilisation platform which used state-of-the-art MEMS gyros, and they're really good to start with, and then they got worse, and then they failed. We send them back, and they send us a new one, and they fail. And in the end, you can't use MEMS gyros in our environment because there's always enough helium in the air. They diffuse into the ultra-high vacuum space, degrade the Q, and they stop working. So now we're using fibre gyros, and that's fine. There's flux motion. Now, everyone's aware of full quantum flux jumps, which you get when your squid loses lock. Yeah, sure, we deal with that. You do good shielding, good RFI isolation, and that problem goes away. But there are other issues we encountered with flux motion, flux discontinuities, which we had to deal with. And we have linear acceleration transduction, that's what I call it anyway, which is, even though the bar is really well balanced, you still get a signal that's proportional to linear acceleration that you have to deal with. And it's equivalent to something like 100 nanometers of imbalance. So when you get to the 50 nanometer level, you might as well stop because you're going to see acceleration signals anyway. That's why we have the other electronic balancing and digital processing methods to help us the rest of the way. And that transduction is different whether it's warm or cold, so it's not something you can easily predict when you're on the bench at room temperature. It's what you make, but it's very reproducible, so we know that what it's going to be when we cool down. And there's been a lot of, I think Brian's mentioned that as well, a lot of component reliability. All of these things and many others that I haven't got time to talk about, we've dealt with. Gotchas, there have been some good ones as well, I have to say. You know, we designed for isoelasticity, and it's remarkably good. It's only 100 ECFOS in a typical line. That's probably better than we expected. So that's a good result. Amazing linearity of the sense circuit. So we can have millions of ECFOS of signal and no harmonics, no distortion. That's a really good result. And that's because we have these mass-produced identical sense coils, and they're really well matched, and so you get the linearity from that. And that same effect also helps you with the temperature sensitivity. We don't need the heroic temperature control. A tenth of a milli-K is all you need, because the material in our superconducting transducers is really good superconducting material. It's good high purity niobium. There are no defects that you find in wires, and so we get that benefit. So that's where we are now since 2010. I think you'll agree that it's been a really dramatic journey, and we're not stopped yet, so there's still a few things to go. What are we going to do next? Obviously, we're going to do more flight testing, and I guess the size of the print tells you how important these jobs are. We're going to do more flight testing. We're going to improve our data processing to get that noise, that processed signal, down to the reproducibility of the signal. And we have some ideas for that already. As I said, we haven't finished processing the July data yet. There's more scope for the future. So processing improvements in getting the instrument data, and processing improvements in doing the geophysical interpretation. I'd be a charlatan if I said I knew anything about that. I don't. I'll leave that to the experts in the geophysics for that. We've got to make slight improvements to the platform. It drifts a little bit after a few hours. It's, we know how to do that too, but it just needs to be done. And modest improvements to the instrument, maybe to try and reduce that direct transduction a little bit. But really, I think processing is where we're going to get our big breakthrough very shortly. Yes, and I guess, once again, as I started with my slide, the team is paramount. I tell you what, I can actually recall all the people. I just say haven't got room to mention them, but I can certainly recall them, and it really has. I'm very grateful to all of the people that have helped in this journey. It's been a fantastic experience. Thank you.
Thanks very much, Frank. So All of the speakers have exceeded expectations on keeping to time, which means, of course, that we've got plenty of time for questions. So if I could perhaps invite the four of you gentlemen up to the front so that you can be in the gaze of the audience. You can see them, but they can see you. And so has anybody got any... Yes?
My question is for Professor Kann. The image that you showed that showed the instrument component with the blurb center, was that pure niobium?
Yes.
Okay.
Well, as pure as we can get in a reasonable time frame and a reasonable cost.
The reason I ask is because I noticed a diffraction pattern on the surface that indicates differential oxidation. Would that be an instrument if that is the plane of which gravity measurements are being taken from, that you have differential oxidation over the surface?
The differential oxidation is to do with the EDM cutting. It just leaves vapor deposits all over the place. You know, I think whatever material you use in an EDM environment, you'll get a coloured pattern.
I'm just
like
wondering
that.
if that's causing any variation in density internally within the instrument.
I don't think so. No, I think the centre of mass stays put quite well.
I mean, if
quite
so, there are
isotropic.
direct correlations between the color you get and the number of microns coated onto the surface of oxidation.
I don't think so, no. I think that's just an EDM artifact.
Okay, thank you.
Oh, thank you. I have a question to Lockheed, Tom. Hi. It was actually the biggest surprise to me to learn that you removed rotational modulation from your latest development. And I wonder, modulation is the only way to get around 1/f noise, right? If you don't have modulations, how you cope with this matter? What has it been replaced with? So that's my
Right.
question.
Improvements in the sensor, and not stuff I'm going to mention here.
But what are you using to modulate your signal? You must have a modulation, sort of.
No, we're not. I mean, it's modulated a little bit just by flying.
Well, that's I don't understand really. Anyway, thanks very much.
Maybe it's got a squid in it.
Hi, James Brewster from Bell Geospace. I've got a question for Chris and perhaps Mark even. I'm just wondering if the filter you called enhanced processing is the same filter that's described in the Dransfield Christensen ASEG 2014 paper that talks about coring and high resolution
yes.
from coring. Is it the same filter?
That was
Yeah.
the first iteration. It's grown a little bit since then, but yeah, that's where we first started using it.
Okay, so it's published there and maybe
Yes.
I'll have a look at that in more detail.
Yeah.
Okay, thanks.
Yeah, this is Des Fitzgerald from Intrepid. While this question might be at Frank, it's not really just a Frank question. It's about the R.J. Smith test range, actually. So I was quite surprised to see you claiming a model response from the test range, because my criticism of the test range is no one knows what the hell the geology is. How the hell can you model it? So how can you show a model versus... it's a philosophical point about the design of that test range. If we know nothing about the geology, how can you model it?
Well, I don't think it matters what the geology is. I mean, yeah.
I beg your pardon? You didn't say that, did you?
That was a crime to say that. But from an instrument perspective, it doesn't matter as long as you have measurements of the gravity gradient. And we have a very fine grid of ground-based gravity stations, and I trust the gurus in the game to upward continue that into a gravity gradient component that we compare ourselves against.
There's only 3,600.
I want you to respond to this.
You've been looking at me funny all day, haven't you? There's only 3,644 stations in a 5 by 5.5 kilometre area. Upward continue that 80 metres, I think we know the truth.
Yeah. Yeah. Thanks, Theo.
Right, maybe that's maybe that one can be continued outside with a cup of tea in hand. Any? All right, I've got a question, Frank. So you said this direct transduction effect limits the balancing you can do to 100 nanometers.
Well, there's not a lot of point in going beyond that because you're going to get that much gravity signal anyway, acceleration signal anyway.
So I can't remember what the numbers were now, but there was, in your little formula, there was a certain ratio you got from balancing.
Yeah.
So what you're saying is that's limited to the 100 nanometers. So really, although you can balance it better than that, there's no point. There's no
Basically,
no
yes.
gain.
So, but the mechanisms for dealing with it are still valid. So the electronic balance, except you've got to be a little bit smarter. It's not just putting on torques because the direct transduction doesn't, follow the right it's too complicated. You deal with it in the methodology is still correct. It's just more subtle than was shown on those slides.
Okay. All right. Thanks. Any other questions? Sure,
Asbjorn Christensen, Nordic Geoscience. Question to Tom Meyer. Tom, exciting developments about putting, on all fronts, but my question is specifically about the digital conversion of the FTG, the DFTG. You mentioned that it's small enough to fit in a helicopter. Have you flown it in a helicopter yet?
No.
Okay.
No.
Anybody else? I've got another question, Chris. This is a general question, but you had a number for the repeatability RMS difference, which I think was 0.6
Yes.
milligauss, and then for the same filter length, but the comparison to ground gravity, the RMS difference was 1.3 milligauss. And this is something I see quite often, and in fact I was quite interested in Frank's talk. There was even a more extreme thing, but I'm pretty confident that Frank's was for a different reason. Any comments about why there's
Why
such a
they're not the
large
same?
difference between the repeatability and the ground truth comparison?
Well, the first hypothesis, that ground station data, while it's there are quite a few points, they've been collected over a period of about 40 years, I think, with the Geological Survey of Canada, and it's also used as a way for students to learn how to go out and collect gravity data. And I'm not saying it's flawed data, but technology has improved over 40 years, and also the repeatability of the lines, it's 14 lines that we get to average the data over versus just one set of flight data. So I think between the two of them, there's going to be some discrepancy between them, but
Can I, maybe I want to ask the question in a different way. Is there any knowledge or feeling for what the accuracy of the ground gravity data is like?
I don't think so. I don't have
Okay.
any.
Maybe if I can ask another, Louise, do you mind, have you any comments on that?
One comment I was going to make is that when you're comparing ground gravity to airborne gravity, you don't always know everything about how that ground gravity was processed, so the terrain corrections, etc. And we found with our cowering data set that was actually made a big difference. So once you've figured out exactly what has been done to the ground gravity, then you can do a better comparison. So that's one thing you might want to look at.
Ian.
Ian McLeod. For all of us who were reading the segment list a few months ago, can you, instrument guys, is there any hope for these semiconductor gravity meters we were reading about? You know what I'm talking about?
Yeah, I do. I think MEMS devices are a potential threat in the wings. I mean, I think there's an instance of a system that's claiming 10 atros per root hertz in a MEMS device. I think if you look at the details of the silicon structure, you'll find that it's not going to be much good in a turbulent dynamic environment, because it's going to have enormous induced dipole error. But that's just a stupid thing, that they made this using the same process to make one that's a sensible shape. And if that was 10 atros, it would...
We're not going to get them in our phones.
We're not going to get...
In our phones, it's a joke.
Yeah, I think there is potential there. I don't know whether they'll get much beyond the 10 atros level with something that small. As Tom pointed out, baseline is everything, and when your baseline is this, it's pretty tough.
I'd be curious to know if you think there's a useful application for having them in your phone. Please share. We'd all be interested in knowing that.
Pour the liquid helium into your phone now.
It's more of a question following up on Frank's answer. So you mentioned about dynamic mode of the MEMS sensor. Does that mean in the stationary mode, it could actually achieve what it's supposed to do? I know we're in the AGG workshop.
There's a publication, or there's some information about a 10 atros MEMS gradiometer. Yeah, I think it's in
Yeah, that's one, but I was wondering from Frank's.
Is that the University of Glasgow?
Somewhere.
Sensor?
It's University of Glasgow are involved, but there's another, I think it's,
Nottingham or something.
yeah, somewhere in the Midlands was
Yeah,
where the
Nottingham.
author
Yeah.
was from.
There's several groups playing with those things.
Those are strictly stationary and open loop in design, not made for use under motion at all. I don't think they would perform at all out of the lab. The fundamental problem with MEMS is any structure, as you shrink it down, it gets much, much stiffer, disproportionately stiffer. The whole objective of an accelerometer is to hold it as lightly as possible. So you have to apply the maximum force to keep it constrained, because that gives you the biggest signal, presuming you know what you're loading on it. So as you shrink something down and it gets stiffer and stiffer, you don't have to do much to it to hold it or restrain it. So some of those papers, they talk about, the key parameter is the natural frequency of the suspension that holds the little tiny proof mass. And, I think I don't even know if they're down to a few hertz yet. There are some ways to get it lower, but they get very nonlinear and sort of dicey.
I had a question for Brian. You talked about your upcoming plans and moving from the Caravan to the Dash 8, and simultaneously with that there was a reduction in noise. Is that noise predominantly due to the more stable aircraft, or are there other reasons for that reduction?
More stable aircraft, easier self-gravity corrections.
Have another go. More general again. I've got two questions. One I know is very quick, but I just wanted to, is anyone thinking seriously about the Bose-Einstein cloud, an instrument based on that? Is that going to be feasible? That's an out there type question. That's one question.
Can you help with that, yeah?
And if there's a response, and I've got a second question if I'm allowed.
Well, does everyone else want to take, I think those trapped atom systems are really, really fabulous, except the vacuum chambers in those things, the last time I looked, they were about this big, and aircraft moves a lot more than that, so I don't know how your trapped atoms are going to go when they hit the walls of the container.
So static application only.
So, for a static application, certainly fantastic. There are people working on ideas for mobile applications. In fact, one of the systems has been flown in an aircraft. And I hope that there's a poster outside on the Bose-Einstein technology.
just an update.
Right, so
We've got designers in there.
Actually, do we have somewhere in the room, somebody,
Yeah, John Close.
is John here? John's not here. You're here? Would you like to comment? No, I'll just bring the mic down.
Yep. So I'm Kyle Hardman. I work at ANU. I'm with the cold atom gravimetry group. So it's a long answer. So I guess if you want to know, you can just come talk to me during the poster session.
Do you want to do a couple minutes?
Yes,
That's fine. And then here we can come.
they will be feasible. And I think over the next 2 years, we'll be designing the system for essentially laboratory-based, but size, weight, power to be mobile, based off of Bose-Einstein condensates. So, yeah, I think they're totally feasible and should be pretty simple to implement.
So,
Thanks, Con.
Lockheed Martin has shadowed and actually worked with Mark Kasovich and AO Sense, who for a long time and may still be the premier folks working this problem. We actually own a gravimeter made by them. I think it's a thing where you know, the further you improve it, the harder it gets. The same as what we see here. The logarithmic sort of improvements, you know, that's getting to the really tough part. Those giant strides at the beginning are not the tough part. Putting these things or anything under motion, this better than part per billion sort of challenge. Any dynamic environment, thermal, motion, pressure, everything. Just the compounding of the problem is it's unfathomable for a long time.
I might add a little comment of my own, because I think what Frank and Tom has said is absolutely right. Gradiometry is a tough business. But I would also add, and I'm sure Kyle would agree with this, is that over the last, I don't know, maybe it's a decade, there have been some pretty astounding advances in the atomic optics cold atom technology. So it's definitely a space to watch, that's for sure. Des, you had a second question?
Yeah. It's about the platform. And just from just practical experience type question, we seem to be running into helicopter half hertz. And you know, how the hell do we get through that? No one's game to give out data that goes below the half hertz, you know, it's higher frequency than that because of the constraint of the helicopter and the blades and all the rest of it. So it's a general sort of observation from looking at data for the last 10 years. We always seem to, you know, and then for mining, you've got to get higher frequency than half hertz if you want to crack anything below 250 metre wavelengths. You know, that has been a bit of a barrier, and I'm saying, how the hell are we going to get through that? Is it going to be a different platform, or are we going to stick with the helicopters, or is there some other idea coming through there? It's a Dorothy Dix question to try and stimulate a bit of answers.
I think it's a good question. I have a feeling that there's the gentleman at the front here probably got a few things to say.
Who wants to start? I mean, we've showed the half a hertz because that improves the noise a little bit. There's nothing to stop us from opening the bandwidth to 1 hertz and sampling it at 2 hertz. You know, and
No one does.
we don't because, well, you know, I think you could do that if you demonstrated the need to do so, and I think I wouldn't be bothered to do that until we get the noise down a little bit. Then it makes sense to open the bandwidth a bit more. The noise isn't really wide. It doesn't cost you that much to open the gate a little bit wider because the noise is going down with frequency anyway.
We've never seen survey data from you. We're interested in someone we see survey data from.
Well, maybe I should respond to the survey data question. So there's 2 parts to that. First is that as Tom mentioned in his talk, the current technology is all modulating technology, so this on this rotating wheel. And so fundamentally you can't get data at frequencies higher than that wheel rate. So that pretty much answers your half hertz right there. You really, if you want high frequencies than that, then that's why I said, in fact, these gentlemen might have some comments on that, because they're the guys who are actually building instruments, all three building instruments that won't have that fundamental limitation. So if they're successful, then we will end up with high resolution instrumentation in the future.
So, like Mark said, I mean, there's two ways with our approach. I mean, spin it faster. But that, that introduces problems beyond some point. Or stop it altogether. On paper, you have infinite bandwidth. I mentioned 1.5 hertz is the upper corner. It's really set to 5 right now. So 0.1 millihertz to 5 hertz. I put the 1.5 because, I mean, talking with Mark, there's not much to get beyond that. So, but it's adjustable. And we have collected data on current systems after their performance on the flight simulator has converged. We've put them in modes where we stop rotating, and we've collected high rate data, and it's been some of the best data we've ever seen. This has been a little while now, and it's part of the motivation for the FTG Plus.
Question for the instrument expert. So theoretically, is there understanding as to the ultimate limit of what level we can measure with precision with current understanding of physics and some estimate, I suppose?
Yeah, I think milli-etvos systems are around. If you don't want to shake them around, you can do that down to milli-etvos kind of levels in a reasonable bandwidth. Spaceborne systems achieve that kind of performance, I think. But you make that design decision right at the beginning. You're designing this device to be operating in a 10 orders of magnitude dynamic environment, and so the things that you do to achieve that means your white noise level is deliberately elevated from the squids are good for a milli-etvos per root hertz in the same size package, not doing a heroic thing with increasing the baseline and all that sort of stuff. That's the kind of trade-off we make. We allow the white noise to come up in order to be able to deal with the dynamics of the situation.
Thank you so much.
Right, I think in setting our goal for FTG Plus at quarter E squared per hertz, pretty much puts things like terrain compensation at the forefront, not the instrument.
Yeah.
So, I mean, cutting that by a factor of 10 again is seems kind of pointless. Is there a limit to what we can do? Yeah, I mean, it's based on the core sensor, which is one of the reasons we've made some improvements to it.
I guess there would be 4D applications, though.
All right, so I'm sorry, I can see I can see a couple more hands going up, but it's time for morning tea. So I would encourage you to talk to the speakers during morning tea, and also go and have a look at those posters. They're all just outside the door. Thanks very much, everybody.